Welcome back. Homework is due today. That homework was write some code to compute the Hamming weight of the binary representation of a number. Lots of different ways to represent a number. Here it is in hexadecimal. We like hexadecimal, at least I like hexadecimal, because it's very close to binary. They're both bases that are powers of 2. That's very convenient. Octal is in that same family. It's base 8. But hexadecimal is really pretty common because each hexadecimal digit is easy to convert into a nibble of 4 bits of binary. And so we can do that. And here's the binary representation of that number up here. Nothing special about it being hexadecimal. It's just a number. This is just a way of specifying a number. We could have written it in decimal. We could have written it in octal. Didn't matter. It's just a value that we're going to do some stuff with. The Hamming weight's the number of ones in the binary representation. So really quickly, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we expect the result to be 16. And this is some C code to do it. How does the C code work? We set our weight equal to 0. We have a loop that runs 32 times from 0 up to 31. Each time through, I go ahead and mask off the lowest bit. I add that to the weight, and then I shift value right by 1, which effectively divides it by 2 and throws away the remainder. Okay. Once I've done that, I've computed the weight and I return it. Pretty simple stuff. And I've got that little C program down here. Let's go ahead and build it. And it returns 16. That's great. Now, if you'll remember, at one point I said the easiest way to write assembly was to write in a higher level language, right, and then compile it. That's the easiest way to get some assembly. Well, let's see what the compiler made of our little solution. And there's what we got. Now, if we didn't have optimization turned on, we'd get something a little different. Let me go through and do that real quickly. Let's go ahead and compile it, and then we'll just dump it out. And we get a lot. This is a lot to take in. Here's the number we care about. That is put here in memory at this address, which happens to be on the stack, in what's called the red zone. We'll talk about that when we talk about the stack. We put a 0 here, we put a 0 here, we then jump down to 2F, swoop down here, we do a comparison with 1F. What is 1F? 16 plus 15 is 31. We jump if it's less than or equal to 31 up to 1F. Okay, that's our, this must be our loop that runs from 0 up to 31. There it is, just literally put in. We then grab this value, which is the first time through the number we care about. We grab it, put it in EAX. We mask off the low bit, just like we did in the code. We add that into this thing, which we initialize to 0. So this must be our weight. So we add whatever the result of that mask was to our weight. Then we go ahead and do this. What is SAR? SAR is an arithmetic shift right. So we shift it right by 1 position. Then we add 1 to this location, which we initialize to 0 up here. And then we compare that same thing to here. So this is our counter each time through our loop index. And we're counting up by 1 each time until we get to 32. When this test fails, we fall down here. We take this value, that's our accumulated weight, we put it in EAX inventory. So that's how that little function looks. It's aside from the stack stuff, it's just a transliteration of our source code. Now, instead of doing that, let's compile it with optimization. And now let's dump it out. And we get something a little different, right? We're not using the stack here. The compiler has figured out it doesn't need to do that. But we should hopefully see the same set of moving pieces. Except now, here we see this. Hex 20. What is hex 20? Well, that's 2 times 16, which is 32. So this is taking the value 32, number of times we want to loop, and putting it in EDX. Interesting. So I would expect to subtract 1 from EDX each time through and watch for the value to hit 0. So let's see if that happens. Let's go down here. Sure enough, here's a sub 1 from EDX, and then a jump, if not equal to 0, up to 18, which takes us up here, which we assume must be the start of the loop, and there's the loop body. All right, interesting. I zero out R8D. Maybe that's going to be the weight. I then put the value we care about in EAX. Here's a no-op. Why is there a no-op here? The no-op is here to cause the top of the loop to be aligned on an 8-byte boundary. And that's a little more efficient. There's a reason for that. It has to do with the way that memory is quote-unquote fetched. So forget about caching and all that for right now, and just pretend that we have to go out to memory and grab some memory. We don't want to use lots of memory lines, so we throw away the lowest lines of memory. And we're always going to grab, let's say, 8 bytes or 16 bytes or something like that. And so when we're going to do that, if we had a non-aligned address, let's say like 11, we would go back and fetch from here and fetch a bunch of stuff we don't care about, and fetch less of the stuff that's after 11 that we do care about. But because we've aligned on an 8-byte boundary, if we're fetching and we get to start at this location, we fetch more of the things that we're likely to care about in the future. So alignment's a good thing, and that's just one reason for aligning it. There are others. It can actually improve the performance of the program to have things aligned. In this case, it's very slight, but it could be there. So the no-op is just here to cause this to be aligned. What if this no-op weren't here and this instruction started at address hex 11? That'd be fine. It would still work, right? There's nothing that would make that not work. The compiler is just trying to be your friend and help you by aligning it. And you can do that in your assembly too. We'll cover that at a later time. So this does nothing, and that takes us to this instruction, where I take EAX, which currently holds the value we're wanting to compute for, and I move that into ECX. Okay, I made a copy of it. I'm probably going to modify ECX, and I don't want to modify this. I want to keep this around to work with later. So I move it into ECX, then I shift EAX right by 1 bit. Okay, that's good. I expected to see that, but I expected that maybe to occur after the masking, but it's okay if it doesn't, because I'm actually going to do the masking on ECX right here, which is a copy of the value in EAX. I mask off that low bit, and so now ECX is going to either hold 0 or 1, right? Because ECX logically ANDed with the value 1 is going to either give me a 0 or 1. I add that into R8D, which we zeroed out up here, so R8D is holding our weight. I subtract 1 from EDX, right? We've already figured out that's our loop counter. And I go on the loop again if I have to. Okay? and then I put R8D into EAX and return. The rules are a little different when we're calling from C. So in our code, what we do is put R8D into EDI, and then set REX to 60 and do a syscall and a halt to exit the program. But this is what the C compiler makes of it, and it assumes it's going to run inside the C runtime. It's going to be our main function. So that's fairly close. There's some things that are a little different here, but it pretty much follows our program. You'll notice that the C compiler has done one of the things I told you it would do. It is doing the work out of order. Up here, we said, go ahead and mask off the low bit and add that to the weight, and then shift the value right by 1. The C compiler has decided that instead of doing what we asked it to do, it would shift the value right by 1 and then mask off the low bit and add it. So it's reordered our workflow. And you're going to see that if you look at a lot of compilation and disassembly, you'll see that happening all the time. The compiler is always trying to make these little changes, especially when there is a memory access. When there's a memory access, often the compiler is desperate to shove quick code up against that so that it can run that pipeline in parallel using speculative execution while the very slow memory fetch is happening. So we'll see the compiler doing things like that all the time. But this is a good example of it for really a very simple program. Now that's not what my solution looks like. So I wanted to write a solution that would look very similar to the things we've seen already. I took the same template I gave you, and I added my code to it. So here's the comment, compute the Hamming weight for the number in RAX, and here's how I do it. I set RCX equal to 32. This is going to be my loop counter, and so you might think that later on what I'll do is I will subtract 1 from it, and in fact I do. So this is decrement. So instead of saying sub RCX1, that's perfectly fine. But here I've introduced you to the decrement operator. It's also an increment operator. Decrement and increment do just what they say. Decrement subtracts 1 from this. Increment adds 1 to this. So this is going to subtract 1 from RCX. Set the flags. And then I can check to see if I've hit 0. And if I haven't, I go back to top and run through this again. We'll talk about the little dot here on labels at a later time. For right now, it's just a label. Don't worry about it. Okay, great. So that's my loop. And then what do? I shift RAX right by 1 bit. I then do an add with carry, RDI, and 0. What? How is that going to work? Well, here I'm adding 0, but I'm also adding the carry. How did the carry get set? The carry got set because when I shifted the low bit into the carry flag. And because I happen to know something about the way Linux starts my program, I haven't set RDI to 0 because I know it's going to be 0 when I get here. Now, playing a little loose here, maybe I should have been defensive and set it to 0, but I didn't. It's great if you did. That's awesome. This is a little shorthand on my part because I know something about how Linux sets up the registers before it calls my program. Decrement RCX, jump back to the top. So this is really it. 2 instructions in the body of it. Shift it and then do this add with carry. So when I shift it, this is going to set or clear the carry depending on what the low bit is. This is going to add that into RDI. Then, of course, since I've used RDI here, I don't need to do anything else. The result's already in RDI. I put 60 in REX. I do the syscall and I halt. And that's it. And so let's go ahead and build it. And let's try it out. We get 16. Nothing too super fancy there. It might be worth taking a look at it in GDB, just for fun. So we'll set our layout to regs. We will start I, and here we are. And you can see we're about to move that value into EAX. Now, in my code, I said RAX, but the assembler was able to figure out, because of something called the zero extend rule, that we'll talk about later, I promise, it could use EAX instead of RAX. It's going to do that a lot. That's why we have a strict keyword to force it to use RAX, but we don't need to worry about that here. The assembler is correct. So it's going to put this value in RAX, and so we'll go ahead and skip over that, and sure enough we see that RAX is now set to that value. There it is in hex, there it is in decimal, right? It just contains a value. Right? Some bits of this register got set, and they can be interpreted as this number in hexadecimal, this number in decimal. Those are the same. RIP changed, of course. It advanced here, and the flags changed. Okay, so let's go ahead and skip to the next instruction. We're going to put 20 in ECX. Remember, 20 is 32. We're going to put that in ECX. And so sure enough, RCX is now 20, which is decimal 32. RIP has changed. Now we're going to shift RAX right by 1. What are we going to get? Well, E over here is 14. 14 is even, so we know that we're going to get a 0. Right? We could have looked at the decimal. It's 0, it's even. We're going to get a 0 in the carry flag, which means over here in E flags, the carry flag will not be set. We won't see CF come up. Let's do that. So we see that this number changed. It's been divided by 2. Sure enough, the carry flag did not show up. That's fine. Now we're going to add with carry into RDI. So where is RDI? There it is. It's currently 0, just like I expected it to be. So we're going to add 0 into it. And we do that, and it doesn't change, so it doesn't highlight it. We know that adding 0 to this thing results in the value 0 being in RDI, so we should expect the 0 flag to be set. And look at that, the 0 flag is in fact set. In fact, the parity flag is set, which tells me that there's an even number of ones in the low byte. How many ones are in the low byte? Well, the low byte is set to F, so there's 8 ones. So it is in fact even. That's great. Now we're going to decrement RCX. So RCX right now holds 32. When I decrement it, it holds 31. The 0 flag is not set because it's not 0. So now when I do this jump if not equal, it's going to check the 0 flag. It's not set, so it's not equal to 0, and it's going to go back to this address up here. So we'll do that, and there we are. Now we're ready to shift RAX to the right by 1 again. Now the low bit is a 1. We can see that because this value is odd. So we're going to get a 1 out of this, and the carry flag will be set over here. So let's do that. And so this got divided by 2, with the remainder being thrown away. Well, actually, the remainder ended up right here. It's the carry flag, and so the carry flag is shown here because it's in fact set. So the carry is set to 1, and now I'm going to add with carry 0 into RDI. It's right up here. It's currently 0. After this, it should be 1, and there it is. And so now you see it's been set to 1. That addition didn't result in 0. The 0 flag is not set. It didn't cause a carry, so the carry flag is not set, etc. Decrement RCX, and go around the loop again. Now, we can do this all day, but let's go ahead and set a breakpoint right here. So we'll B at this location if RCX is equal to 1. And now we have a breakpoint. Notice I had to put the little asterisk in front of that. And in order to use my arrow keys, I had to use the Control X O to get my focus back down here so the arrow keys would work on here. Kind of annoying, but that's the way that it works. So it shows us a breakpoint right here. That's great. If we do IB, we'll see that sure enough, we're going to stop only if RCX is equal to 1. So at this point, let's just continue. Alright, a lot of stuff happens, and we reach our breakpoint. See, we're at this line. We haven't executed it yet. We're about to. We'll be decrementing RCX. RCX currently holds the value 1. Okay? So, let's go ahead and do that. Now we've decremented. RCX is now 0. You notice the 0 flag got set because we've now, the result of the last thing was 0. So now we're going to do a jump if not equal back up to the top, but that won't happen because we are in fact equal to 0. And so sure enough, we skip to the next instruction. What does the next instruction do? Well, it puts hex 3C into EAX. What is 3C? Well, that's 3 times 16, which is 48. And C, what is that? That's 12. 48 plus 10 is 58, plus 2 is 60. So it's going to put the value 60 in EAX, which is what we want. Sure enough, RAX is now 60. And now we're going to do the system call. That's going to exit. Our return value is going to be what's in RDI, which happens to be the value 16, as we see here, or hex 10. That's the correct answer. We do that, and we see that the inferior process exited with code 20. All right, fine, whatever. So there we have it. We're done, and we got the result out, and that's how the thing works. All right. Let's talk about some additional new tools. I'm not going to spend too much time on this. We have plenty more to do. Strings. Strings is a way of, it's just a command that looks through your file and it looks for things that look like strings. So what about our little Hamming file? Let's just go ahead and try that. And it finds a few. It finds some things that it thinks look like strings. It finds Hamming solution ASM. That's the original name of the source file. So that must have made its way all the way down to here. So that shows you that there is some metadata put in this case, by the assembler and then preserved by the linker that can survive all the way through. And that can be really useful if you're looking at something like a piece of malware. If someone has not done a good job of scrubbing their malware or forgotten to do it, sometimes you can find interesting stuff like this present in it. We see the symbols. So here's start top, BSS start, eData end, a few others in here. These are the names of sections in the file. Text came from the assembly. These come from put in by the assembly and linking process itself. We'll cover those later. So there we go. Symbols that were in our Hamming solution code. What about the stuff we got out from the C code? Are there any strings in it? Oh yeah, there are lots of strings in it. So we can go back up here and we'll see that sure enough there's this, which is really important. It shows us the libraries. It shows us the version of the libraries. Some things are probably not actually strings, okay, like this, This thing right here is probably just a sequence of bytes that looked like a string. They were in the ASCII range, terminating null. It looks like a string. I'll print it out for you. We'll notice that, sure enough, look at this. It tells us GCC was used to compile it on Ubuntu, and here's the information about that, right? Ubuntu 2004. There's some information. Again, lots of information when you dig into these, if people will leave that stuff lying around. All right, and then lots of other stuff in here. So that is strings. In addition, you can add this -tx, and that tells you where it occurs in the file. So if I said strings -tx, it would show me the offset, in this case in hexadecimal, of that location. If I just do -t, it'll warn me and tell me, here's how you specify it. So I can get the decimal offset like this. But don't want to see hex. All right. That's strings. And as I pointed out, it's not perfect. Right? Sometimes you get gibberish. A more direct way of doing it is to actually look into symbol tables that are present in the file, and that's what name does, nm. So let's go ahead and run nm on our little file. Hamming solution. Okay, and it shows us the offset, but it shows us the address. But it also shows us these little symbols, and it shows us this character right here. This tells us something about the section that it came from. This is like an abbreviation of that. So these all came from the text section, and in most cases an uppercase means it's global, and a lowercase means it's not. So start is a global symbol. Start top is not. Are there any names present in the symbol tables of the C code? Sure, there are tons of them. Lots of stuff. And again, we can look through these and see if there's anything in here that's interesting to us in terms of figuring out what the code does. The point of this is sometimes simple tools, the simplest tools, can actually reveal a lot about a program. Some compilers, Windows compilers, will put information in there about when a thing was compiled. Some assemblers will put information about when a thing was assembled, the platform, assembly options that were used, etc. And so a lot of times you can pull some information out. Now, of course, if you don't want that information in there, there's a tool to get rid of it. It's called strip. And let's strip our Hamming solution. And now, what's in Hamming solution strings? There's still a couple things there, right? We need to know where the text section is, and we have this shared string table, which is going to be empty. It's not going to be empty. It's going to contain these two strings. And let's run name over it. And it says no symbols. So we've gotten rid of a lot of information and made the job of a reverse engineer much harder in terms of figuring out what this does. Let's cover a few more things from the instruction set architecture. So we'd gotten to this, but hadn't quite gotten into it. This was the next thing to talk about. This is going to be a little confusing, but just bear through it and you'll be fine. I think once you sort of figure out what's going on, it turns out it's not that complicated. It's actually fairly simple. The assembler is going to do a lot of the heavy lifting for you on some of this, and we'll talk about that. It's going to just be a little bit confusing. If you set the lower 32 bits of a 64-bit register, then the upper 32 bits are automatically zeroed out. This is called 0 extended move. So I do a move, and I put 17 into EAX. And we know EAX is a name for the lower 32 bits of RAX. So really this is just saying set the lower 32 bits of RAX to the value 17. And 17 fits in those, so it's just fine. When you run this instruction, it will in fact set the low 32 bits to hold the value 17, but it will also zero out the high 32 bits. So this effectively sets RAX to 17. Now why I do that? Takes fewer bytes. If I wanted to set RAX, I would probably need to specify an 8-bit operand over here. So that, 8-byte operand over here. So that would take 8 bytes to specify the value 17. If I just use the D word, then I only need to specify 17 with 4 bytes. And I save those 4 bytes. Shorter instruction that runs faster. Life's great. Okay. In fact, this is so common that the assembler will automatically convert the instruction for you. It's part of the assembler's optimization. Remember, everything in the computer is trying to figure out what it thinks you really meant and fix your work for you. And the assembler is no different. So here we have move 17 into RAX. What does the assembler make of that? It says, oh, you meant move, and hex 11 is 17, move 17 into RAX, into EAX, and let it be 0 extended. It fixed that for us, okay? We don't want that, so we say, no. I mean the quad word 17. Move that into RAX. The assembler says, okay, great, I know what you meant. I fixed it for you. The only way to overcome it is to say strict. So move RAX strict 17, and so now we get the full, you see here, there's the low order byte, so that's 17, 0, 0, 0, 0, 0, 0, 0. So it's 8 bytes of 17 into RAX. And there's that weird move ABS that comes up sometimes. Alright, so now it's kept it. And I could say Q word here if I wanted, and that would give the same result. So strict is what you would need to do that. Why would you ever need to do that? If doing this is better and it 0 extends, why would you want the 8 bytes? Well, you might want the 8 bytes because of alignment. It might turn out that that conveniently gives you the alignment you want, and that could be a good thing. You might want the 8 bytes because you want a place to write some stuff later on. That's the best way I can say it. And there are a number of ways to do that. For example, I might do this and define what's known as a relocation, and we'll talk about that when we talk about ELF files. A relocation that will then overwrite this with a full address. Or I might have a sneaky way of modifying my own code, self-modifying code, and I might want those 8 bytes because now I have more room to maybe put some extra instructions in here or do something really, really bizarre. Lots of reasons. Some of them good, some of them nefarious. For the most part, it's not a good idea. You really do want this, and that's what the assembler will try to give you. Alright. The 0 extended move only works in that case. Suppose I wanted to take what's in BX, which is a 16-byte register, and put it in RAX. Will this work? No, it won't assemble. Why not? This is a different size from this. Don't do that. Won't work. Okay, here's a 32-bit thing and a 64-bit thing. Nope, won't work. Can't do that. Don't do it. What if I go get a word from memory and try to put in RAX? Won't work. These are different sizes. You can't do it. If you would like to take something like this and put it in the larger register and 0 extend it, there is an instruction that will, in fact, do that. And it's move ZX, move 0 extended. Okay, this will explicitly zero out the high bits. So now I can do this. If I take BX and I move it with 0 extension into EAX, right? This is a 16-bit register. This is a 32-bit register. This will zero out the high 16 bits of this register. What about the high 32 bits of RAX? What happens to them? I'm not gonna tell you. I want you to figure that out for yourself. Okay? Remember, there are two rules here. One of them is the 0 extended move will 0 extend the thing right here to hold this value. And the other one is that when you set the low 32 bits of one of these registers, you 0 extends into the high 32 bits. So that would seem to indicate that this will in fact set RAX equal to BX. In other words, these two instructions are the same. But are they? I will let you go and figure that out for yourself. I think it would be worth you trying to figure out how you can see if that's true. Write some code and run it in the debugger. All right. This clearly zeroes out the high 48 bits of RAX, right? Because this is 16, this is 64, and so the difference is 48 bits. All those get zeroed out when you set the low 16 bits. This also is 16 bits, so it zeroes out the high 48 bits. Right? This is just an address. We go and get the word with the 16 bits at that address. Our address is 64 bits. We get the 16 bits that are stored there, and we put them in here and zero out the high 48 bits. Great. So this is 32 bits. It's 64 bits. I'm going to move with 0 extension, and that won't assemble. Why won't that assemble? It's because the assembler wants you to use that. This has exactly this effect. So if I move EBX into EAX, that's a 32-bit register I'm setting. It's going to zero out the high 32 bits of RAX. It's the same as if I could do this, but the assembler won't let me do it. I have to do this instead. So there's always an exception to everything that looks like a nice general rule. Just get used to it. You may have noticed that I always used registers here. I didn't put 17 here. That's because move ZX only works with registers. So I can put registers here, or I can put memory here. I can't put a literal here. Registers and memory. This doesn't work for signed values. And you can, I think, figure out why. So let's say I put the value negative 17 in BX. What does negative 17 look like in 16-bit 2's complement? Because this is a 16-bit register. It looks like 0xFFEF. That's what it looks like. So then I do this. This does not affect the high 48 bits in the right way. It zeroes them out. So now this thing holds 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, FFEF. The sign bit is not set. The value in RAX is a positive value. And that's not negative 17. That's not what we want. So what do we need to do? We need to extend the sign bit. So the 2's complement representation of minus 17 is that. The 2's complement representation of minus 17 in 64 bits is this. So notice what happened here. The sign bit is the high bit here, and I just smeared it right across here. And that's how I end up with the minus 17. The sign bit has been extended all the way over here and filled in. And that's how I get a minus 17. So sign bit extension. There must be instructions that do that, and there are. Similar to move ZX, there's a move SX, move with sign extension. There's a sign extended move. So now when I put minus 17 in BX, and then I put BX into RAX here, if I use the 0 extended move, I get a positive or unsigned value in here with a bunch of zeros in the high bits. If I do a sign extended move, I get a negative 2's complement value in here with a bunch of 1's in the high bits. And there you go. Now, this seems like this is going to be just perfectly symmetric. These two seem like to be very much the same thing. But, of course they're not. This is the x86. Unlike MoveZX, there is a version that will move a double word to a quad word with sign extension. Remember, I couldn't say move ZX, RAX, EAX. I couldn't do that because I had to just do move EAX, EBX. That's what I had to do. And let the 0 extension rule work for me. Well, there's no default sign extension rule, so that won't work. So there should be one that lets me say move SX, RAX, EBX. That would be great, but there's not. Or is there? Well, there is, but it's got a different mnemonic. It's move SXD for double word. Okay, well then it would be great if there were a move ZXD that looked just like that, and there's not one. That's really annoying. But the good thing is, in this case, NASM will help you. If you do accidentally write move SX with RAX and EBX, it'll go ahead and fix it for you. It'll convert that over to move SXD. NASM will do that. Not all the symbols will do that, but NASM will. So let's take a look at the crazy up close. So minus 17 into BX. Look at that. There it goes. BX into RAX with sign extension. There it is. Minus 17 into EBX. There it is. Notice how we have more ones up front here because now we're in a 32-bit number. Move EBX into EAX. That will 0 extend into RAX, and so we end up with a positive value in RAX. And there it is. And then move SX, so sign extended, EBX into RAX. NASM knows what we mean, and so it fixes that into move SXD. Or we can be explicit, and it will just do what we said. Whew. All right. Most important part of that is to remember that if you set the low 32 bits of register, you will zero out the high 32 bits. It's a convenient way to use fewer bytes. Let's talk about system calls. So we've used syscalls in a bunch of listings that we've seen. What are they doing? Well, there's an operating system that runs at a high privilege level. It runs in what we would call ring 0, where it has access to a lot of the machinery of the processor that we don't get to have because of security. So a system call says, I want the operating system to do something for me. And in order to do that, we have to transfer control to the operating system in the call handler in ring 0. That's a context switch, and it takes some time from user space to kernel space. In fact, it can be slow. There are fast system call extensions that move some of the system call machinery to user space. All of that's just time. We'll talk about that as just time. But for the most part, a system call is going to interrupt the processor, tell it to do a major context switch, and then run something in ring 0 based on information we provided. Okay. If you've done 32-bit Linux programming, it's int 80. If you're a Windows programmer, it's int 21 hex, and it varies depending on the operating system. But there you go. Syscall is the instruction in the 64-bit world that causes that context switch to happen. And in fact, syscall is a fairly complicated instruction. If you go and look at the details of it, you'll find a surprising amount of complexity in what would otherwise have just been an interrupt in previous versions. You can read about the Linux system calls in Chapman's blog post. I tend to like to use this. It's convenient and simple. It gives you a pretty straightforward way to look at them. If you want to look at them on different platforms like the ARM and so forth, you can go and look at the Chromium documentation, and it will give you a list of them. So here is the Chapman blog post I mentioned. It's from back in 2012, but it's really good stuff. And as we scroll down, we start to see the list. We'll have to stretch it a little bit. And so here's syswrite, and we see the register names up here at the top that we would set for the syswrite call, and then what goes in each one. And this is just a quick summary of all of the system calls, and you can see there are quite a few of them. Alright, so here's how you do a system call. You load RAX with the number of the system call. For example, exit is 60, write is 1, etc. And really there aren't that many, so you don't really load RAX, you load EAX and let the number 0 extend into RAX. You load other registers with arguments to the system call. Those other arguments go in RDI, RSI, RDX, R10, R8, and R9 in order. So if a system call had 3 arguments to it, they would go in RDI, RSI, and RDX. You can only pass 6 arguments to the system call. That's it. Each one of those is 64 bits, so you could pass a byte or an int or a full address, like a pointer. You invoke the syscall instruction that transfers control to the operating system that then fulfills that system call. If the system call returns, the return value will be in RAX. And some don't ever return. Exit is an example of a system call that never returns. There are others. The point of all this is, to understand an assembly program, you have to be very conscious of the size and the representation of your data. This is sort of the punchline for all the things we looked at in the last class and the beginning of this one as well. You really have to think about, okay, this is 32 bits, this is 17 bits, this is whatever it is, it'll fit in this register, I'm going to do this stuff with it. The math I'm going to do won't overflow the register, or maybe it will, I have to check for that, etc. There's a lot of things you have to be very explicit in thinking about in assembly. So let's shift gears a bit and talk about writing assembly. And let's write a Hello World program. We actually now finally have all the pieces that we need, almost, to write a Hello World program. We're going to have to introduce some new stuff, but this is a good way and good time to do it. So here's the Hello World program. It's over on the right hand side, and it's pretty straightforward, I think. It uses the syscall to do the write. It uses the syscall to exit the program, so there's 2 system calls. One of them is system call 1 for write. The other is system call 60 for exit. Our exit value is in RDI, which is the first and only argument to exit. And up here we have the different arguments we talked about to write. Let's go through this piece by piece and look at all of it. First, we'll take a look at the data. So down here at the bottom, we have something that says section data. Now we're going to talk in detail about what sections are, but for right now, let's just say that a section is a contiguous block of instructions and data. And in this case, it's just data. And so what's in there? Well, we have this message, hello world, new line. A new line is an ASCII 10. NASM does not know about /n, so we'll just stick a 10 on the end. That's fine. So this is a series of data bytes. DB is data byte. There is a DW. There's a DD for data double word. There's a DQ for data quad word. Different ways of specifying data. Data byte, because specifying bytes, we can take a quoted string like this, and it will convert that into the sequence of bytes to represent that string. Okay. And message is a label. So message is a label whose value, when it occurs up, let's say up here, is going to be the address of this capital H. The first character of the string be the address of that. This does something a little different. This defines a constant. This isn't technically a label. It's really a constant, so there's no colon here. There could be. NASM is pretty forgiving if you put a colon there, but it's really a constant. And I'm defining this constant to be equal to this. Now, what is going on here? Well, we know that message is the address of this capital H. $sign is sort of the, let's call it, current position in the stream. Well, we just had message, so the current position is right after this 10. It's the first address following the string. So if I take the first address following the string, which is $, and I subtract this address right here, I get the length of the string. Pretty cool, huh? So this allows me to set the constant len equal to the length of this string. Because right doesn't use null terminated strings. Right, you have to specify the length, so we need to get that. All right. Now, all of this stuff you see right here, this is NASM syntax. If you were using the GNU assembler, it would be different. Okay. NASM syntax. So let's stop and talk about sections. So here we have a section right here. Section text. So the idea is that everything we see in here is going to be in the text section. And we see some instructions here. Right? Could be some data in there as well, but there's mostly just instructions in here. A section is a logical group of instructions or data that have the same access controls. Right? They're read-only, or they're executable, etc. And you can have any sections you want. The period sections, the ones that start with a period, are reserved for the system. Now you can have your own period ones, but you run the risk of conflicting with something defined by the system. So these are the common ones. .text contains executable code, and it's not writable. On some platforms it is. But on x86 it should not be writable. Data contains read-only initialized data. So go back here, look at this. Data contains read-only, we don't need to modify this string, initialized data. Since it's read-only, it better be initialized. We can't initialize it because we can't write to it. All right, so it's read-only initialized data. BSS, what is BSS? Block started by symbol. I don't want to explain it. It's just whatever it is. Is writable, uninitialized data. So really, when you have a BSS section, you're allowed to reserve bytes in that section, and there's a special NASM directive for doing that. But you can't put initialized data, you can't put instructions and stuff in there, or the assembler will complain. RO data is a read-only data, another section for read-only data. There are lots of these. These are some of the ones that are most common. What if I don't want to do that? What if I just don't like playing by the stupid rules? I want to make up my own rules, right? What if I don't want to do that? So if you're one of those people that insists on having a pet ferret in California or breaking the rules in some other terrible way, you can do it, right? Everything's by convention, so sure. So here you see I have a section called stuff. Now because it's not called .text anymore, NASM doesn't know what properties to assign it by default. And so I have to say, hey, it's going to be executable. And oh, by the way, please align it on a 16-byte boundary. So I specify this. I recommend you take this code, you remove this exec, and you try to assemble it and run it and see what happens. It's always worth doing the experiment. So here's my stuff section, and it's got some code in it, and then I have a section called more stuff, not executable, not writable, and look, I put my data in it. Here's my data. And then I have section stuff down here with some more code. The heck? Can I do this? Is this legal? Totally fine. This is totally fine. So what happens when I start running the program and I run these instructions and I get here, what do I do next? Well, the next thing in the stuff section is here. And so I do this code, right? This and this are going to be in the same section. They're going to be contiguous. And this stuff is going to be in a different section called more stuff, and it'll be somewhere else. Just how the assembler will lay things out. Okay. All right. Nothing magical about the names. Use the standard names because you don't have to say all this other stuff at the end. Right? Text by default is going to be executable and not writable. Data by default is going to be not executable and not writable. So on. It's going to know those. So you typically want to use the known ones. But you can use any section names you want. It's perfectly fine. We can see our crazy section names in objdump, so I go ahead and assemble it, and then I objdump the .o file, stuff and more stuff. There they are. Name of the section. And the size, so up here we see that it's hex 28. 2 times 16 is 32, plus 8 is 40, so it's 40 bytes. That's 14. So there you go. It's assigned some space to them. They have a file offset. This is where they occur in the file, in hexadecimal. We did tell it to align our stuff section on a 16-byte boundary. 2 to the power of 4 is 16. I didn't tell it anything for more stuff, so it says stick it anywhere. Okay. This information will be used by the linker. The job of the linker is going to be to assign addresses to things so that they can be linked together. Right now, if you look back here, you'll see these fields are all zeros. We'll come back to those after linking, and they will hopefully hold actual addresses. Right now they don't. The linker will use this information to figure out what addresses to give them. And then we have flags. Lots of flags. And so notice that for stuff, we have the code flag. It's executable and read-only for that. And then for more stuff, which is our data, we have read-only, but we don't have the code flag. Okay. Now, once we have linked it and we have executable, you'll notice a few things have changed. In particular, this points out that the relock flag is gone. There's relock. Now it's gone. Okay. And we'll talk about what that means at a later time. It just means there are relocations present, and we will spend way too much time talking about what they mean. All right. We also notice addresses. We have actual virtual memory addresses. So what do I mean by virtual memory? We have paged memory on a modern processor. And an address here doesn't necessarily correspond to a specific address in physical memory. In fact, it doesn't. Right? This address tells me where to look in a page table to find a page of memory that may be backed by some physical memory. It might not be. It might be backed by a device or something else, but it tells me where to go and find that in the page table. Okay. There are other platforms where there is this direct correspondence to physical memory. The x86 and the ARM aren't those kinds of platforms. They have page tables. We'll talk about how virtual memory works later on. Right now, just don't worry about it. It's just an address. Don't worry about the address. That's our virtual memory address. This is our load memory address. This is where should I load this code? Well, why would these two ever be different? Well, without getting too deep into it, if I'm doing something where I'm putting some code in ROM and then later I copy that code into RAM to run, they might be different. For our purposes, they will always be the same, so don't worry about that. The GNU compiler suite and all the tools, they run on everything from, bare metal 8-bit microcontrollers all the way up to, modern fancy microprocessors. So there you go. So we have some addresses now, and in particular we have a very, very important address called the entry point. Entry point's an important concept. Stick this in your brain. Remember it. The entry point is the first address to execute when your program is loaded. Okay? So think about that. My code's stored in this file. I tell you how to lay it out in memory, right? Because I have addresses, so I tell you what goes in memory. But then once you've loaded it into memory, where do you go to run it? You go to the entry point. By default, the entry point is defined by the _start symbol. And that's right here. And so we just start running this code. There you go. That's our entry point, the address of the first instruction in the program to execute. And it's by convention _start. Well, that's a convention, right? And, I want to own ferrets in California. I want to, smoke within 10 feet of the gas pumps. I'm going to flout convention. Sure, why not? Fine, go ahead, do that. Suppose I wanted to call it first and make that a public symbol so it's exposed. I could then tell the linker, hey, by the way, the entry point isn't _start like you expect it to be. It's first. Why would you do this? I don't know, but you can. The common way to do this in cases where you actually want to enshrine this kind of linker foolishness is to write a linker script. Now, I'm not going to talk about linker scripts because that's way beyond the scope of this class. But if you are one of those people that just has to know in an LD linker script, you would specify it this way. So there you go. Enough said about that. Not something I expect you to ever need to know or need to do. Just be aware that there may be weird cases where people have defined things in weird ways. And sometimes, this is sort of the low-hanging fruit that's not going to fool anybody. Once in a while, you see someone trying to do that to trip you up. Let's use objdump to find the entry point of executable. So we say objdump-f. That gives us the file headers. And it tells us, our hello program, that's what we're looking at, is a file format ELF64, x86, 64-bit. Great. The architecture is just what we think it is. There's some flags. We'll talk about those at a later time, maybe. Executable has symbols and it's paged. Here's its start address right there. That's the VMA, the virtual memory address of the entry point of the program, the first instruction to execute. And if we look at the symbol table, which we can do with objdump-t, we'll see a bunch of symbols, and one of those will be start. And there's start, and look at that. The value of start is over here, and that value is that value. There you go. Boom. They match. We notice it's a global symbol. That's what the G is for. It's in the text section, and its length is 0 because it's really just a symbol that holds the number. Okay. There you go. We'll walk through that. There's a video I think I'll post where I'll walk through the symbol and string tables. All right. We've beaten the daylights out of sections. Let's go back and talk about that right. So here we are. We have our write system calls number 1. Standard output is 1. Our message is stored at this address. There it is. So I move the address message into RSI. I put the length in RDX. And I do the system call. So is that right? Command page for write, I will find out that it has this function prototype. It takes 3 arguments, a file descriptor, a pointer to a buffer to write, and a count, a number of bytes to write. And I know that arguments have to go in these registers in order. Since there are 3 of them, they have to go in RDI, RSI, and RDX. So the file descriptor has to go in RDI, And in fact, we do that right here. We put standard out, which is 1 in RDI. A pointer to the buffer, the address of the buffer, has to go in RSI. There we go. We go ahead and move message, which is the address of this initial H, into RSI. And then the length has to go in RDX. And so we take the constant length and put that in RDX. You could almost think of this length here, which is a assembly time constant, as just a macro. It's going to be whatever the assembler worked out the length of the string to be. So once they're in RDI, RSI, and RDX, we can then do a system call, and that will write out the message. There you have it. There's my system call. Let's talk about exit. So again, I go to section 2 of the man pages, and I look up exit, and I find that there is, in fact, a little underscore exit, which takes a single argument. We know that the first thing is an RDI, so our one and only argument will go in RDI. It's void. There's no return value. So we put 60 in REX to indicate exit. We put 0 in RDI for a return value of 0. I do a system call, and there we go. That will do an exit. What does that do? That tells the operating system to remove my process from the scheduler, so I won't get any time to run anymore, and I've been stopped from running. Deallocate my resources, destroy my thread pool, all the other things that have to be done. Release my memory, etc. Call does not return. So, wait. If the call doesn't return, why is there an instruction after it? What is this little guy? Well, this halt instruction tells the processor to halt. To basically stop the processor's oscillator or clock. And so the fetch execute decode cycle stops, the processor just like hangs, and it's done. So that should never execute. Why is it there? That's a terrible thing to have there. Why would we have that there? It's essentially a visual indicator. What does it do when you run it? It's a privileged instruction. Here is some code that we can assemble and link to try it. In fact, by default, it puts everything in text, so we could throw that line away. If we don't have this stuff, it'll assume the first instruction is the one to run. It'll give us a warning. But we could reduce this entire file down to just those 3 characters, and we'd be in good shape. We build it and we try to run it, and it's seg faults. That's because this is going to cause a processor trap or a processor exception. So putting it here at the end is sort of pro forma, and it's kind of defensive programming. If for some weird reason we screw something up and this syscall returns, this will trigger an exception which will halt our program. It's supposed to halt anyway, but this will make sure that it halts. Okay, that's why it's there. Otherwise, we just keep going and plow into whatever random code happened to be sitting after this, which could be just garbage, or maybe this data, or who knows what. All right, good defensive programming. The point of all this is, with the great freedom of assembly language comes the responsibility of knowing way too much about your program. You got to know a lot of stuff about it to make this stuff work. The compiler does a lot of stuff, fills in a lot of gaps, makes a lot of decisions for you, and that can be good or bad. With assembly, you're in charge. You've said, hey, I want to take responsibility for all those piddly decisions that you were making for me. Let me take charge of that. All right. That was a lot to cover. Let's continue on and talk about the stack and procedure calls. Let's talk about the stack. So I've mentioned the stack many times, and this is no different. We're going to talk about the stack some more. Your process has its own virtual address space, which will look like the address space of other processes. Okay? So each process has the full range of addresses available to it, and that's true for every process. So every process can have the same memory addresses. How can that work? Well, that's all handled by the paging system that we'll talk about later. But basically, think of your process as having its own address space. Low memory is down here, 0, what we call it low. High memory is up here where all the bits are on, that's high memory. And you could think of this as just a bunch of stuff. Now, your machine is not going to have memory that ranges from here to here unless it's a really esoteric machine. It's not going to have that much RAM. But that's okay. The virtual address system is going to make that work and make it look like there's memory. All right. So what do we have in there? Well, at low memory, we typically have the program text. It's not down at 0 for technical reasons. And in fact, it's seldom very low. Often it's maybe about a third of the way up. Again, for obscure technical reasons that maybe I'll talk about when I talk more about stuff. So anyway, there's your text. It's typically unmodifiable, and it contains your code to execute. That's usually followed by your data. So your data section has unmodifiable initialized data. That's usually followed by your BSS, which is modifiable uninitialized data. Right? So these guys are both unwritable, and they might even go into the same segment. When we talk about segments, we'll talk about how that works. So don't about that too much right now. These are writable. They might go in the same segment. So modifiable and uninitialized data, your BSS, block started by symbol. Following that, the operating system, not assembly or the processor or any of that, but the operating system may allocate a heap for you. And the heap typically is a chunk of memory, and we say that it grows upward toward high memory. So the heap can get bigger as you need more memory, and it can shrink as you need less memory. The heap can grow and shrink over time. The size of the heap is controlled by the program break, or BRK, and it points to the first unused address. Right? So the heap's up to here, and then we point to this address right here as the program break. Now, the program break is still widely used. The heap is still widely used. These things are all true. But there's an increasing use of mmap. When we talk about memory, we will talk about the complexity of memory. This is a nice, simple picture, if only it was still true. Between the heap and the stack, which is usually at high memory, is free space, a place for these to grow into. This is not always empty. In fact, it's seldom empty. Usually there is something here. On some platforms, there's a canary address here, so that the stack grows down and the heap grows up. They don't collide. Something else happens before that can happen and cause mayhem. Usually a processor exception. Oftentimes, this is where the shared libraries get mapped. So shared libraries can be mapped into this area right here. The stack, we already know, is up here at high memory. It grows downward. The last address in use by the stack, the lowest address in use by the stack, is the stack pointer RSP. It points to that address. So you may see here, we get this and we bump it up one more to this. Here we have this, we bump it up one more to this. When you have a choice, you typically choose the higher address. Okay, so here it's one past the end of the heap. Here it's up here, it's the last address in use in the stack. The instruction pointer, that points to the next instruction to execute. So there's this common theme of all these pointers being moved up in memory. And that's because that address is typically an aligned address. All right. Enough of that. So this is your basic layout. Okay. So with this in mind, with this notion of process memory in mind, and this concept that stacks up here going down, let's think about what's on the stack. So when we push something into the stack pointer address is decremented by the number of bytes And then the value is copied into memory starting at the new address. Okay, bear with me on this. So here we got our stack. RSP is pointing to this last byte in use by the stack, lowest one in use. EAX holds this, and here's our stack pointer. And so I want to push EAX, which is 4 bytes. And so the first thing I do is I subtract 4 from the stack pointer. So if you look at the stack pointer value right here, see it started out A8 and then it ended up A4. We subtract from the stack pointer to reserve space. And oh look, there's some stuff there. Is that the stuff we want to be there? No, it's no resemblance to that. That's just some stuff that was already there. All right, again, memory's going to have bytes in it. And as soon as we've got this stuff, we move the stack pointer, there's going to be stuff there. And so in this case, there's some stuff. Maybe that's left over from some prior computation. Who knows? But there's some junk there. Now we want to copy these 4 bytes, 24, 72, 73, 70, into here. Now we're going to copy it in starting at this address. This is ascending memory. We know we like to store things little endian. Where's the little end of EAX? So it's right here, it's 70. So we'd expect 70 to go here, then 73, then 72, and then the big end, 24, would go here, right at the highest address. And sure enough, that's what happens. So effectively what we did was subtract 4 from RSP and then do a move of EAX into the address pointed to by RSP, and there we have this value now stored on the stack. It's just bytes. I could add anything I wanted to or move the stack pointer wherever I wanted to move it. It's just bytes in memory. Okay, so this push EAX is not exactly equal to these two instructions because these instructions set flags and the push instruction does not. Okay? Otherwise they would be the same. When I pop an item from the stack, what happens? Well, up here we have some value in EBX, and we're going to pop EBX. And it's 4 bytes long, so we're going to take 4 bytes off of the stack. And how are we going to do that? Well, the first thing we want to do is copy 4 bytes starting at RSP into EBX. And so you can see how that's going to go. Here's the lowest, so on, highest. So we're going to wind up with 24, 72, 73, 70 in EBX. We do that, there it is. So it's effectively the same as moving the byte, the D word pointed to by RSP into EBX. Now, stack pointer needs to have 4 added to it. So we do that. And there we go. Now, I leave this here to point out that these bytes are still here. They didn't go away. Okay, they're still here. If I added 4 to RSP, they would now be live on the stack. But it doesn't matter whether they're live on the stack or not. This is just memory, and I can go and reference it, right? I can say RSP, go get me the D word at RSP minus 4, and that would return this value. We call this the dirty stack. If I were doing a computation involving a cryptographic key or a password or something else, I might leave it lying around on the stack. If a caller sort of knows where to look for that, again, the stack pointer, they can just manipulate it however they want. They might move the stack pointer around until they can see this stuff and get access to it. Okay. That's how the stack works. Stack pointer is RSP. It always points to the low byte of the last item pushed. You subtract to reserve stack, and you add to release stack. It's a little bit confusing. Some people think it seems backwards. Just try to put that in your brain and internalize it. Now that we know how the stack works, we're almost ready to talk about procedure calls. So The call instruction is the instruction on the x86 that implements procedure calls. The way that it works is as follows. It pushes the current 64-bit value of the instruction pointer onto the stack. I mean, that's pointing to the next instruction to execute. It pushes that on the stack. And then it loads RIP with the argument to call. So call is basically a fancy way of saying push RIP and then move a value into RIP. We can't literally move a value into RIP. That won't work. But we can use call to have the same effect. And there are different ways to do it. I can call what I'd think of as indirect absolute. Right? So I'm calling indirectly because I'm calling through a register, but to an absolute address. I could call, again, indirectly to an absolute address stored somewhere in memory. So this computes an address, right? Base plus RBX times 8. That's an effective address. And I go and I get the 64 bits or the quad word at that address and I call it. Or I can call it relative by offset. Do it this way. Seldom that I use full 64 bits. Often I'll be able to implement a call by using 4 bytes or by doing some kind of a relative thing. We'll talk about that too. Alright, so there's a return instruction, ret. How does it work? That's easy. It pops the top 64-bit value from the stack into RIP. When we pushed it, it pointed to the next instruction. So once I pop it, it again points to that next instruction, and the fetch, decode, execute cycle just plows right along. Okay, there you go. That's how call works. That's it. That's all you get. Did I say anything about arguments or return values or any of that? I, in fact, did not. So here's the program that has a subroutine. It prints Hello World, Hola Mundo, and Hallo Welt. So it prints Hello World in a couple different languages. Fancy Hello World program. And it's got a subroutine. The subroutine's up here at the top. So the first instruction to execute is not actually the first one in the listing, it's down here. What does this print? What does this print do? So this is a label, print, and we see it does some stuff. Does a whole series of things. There's a system call and there's a return. And then down here below we see we're loading some stuff in RDI, calling print, loading stuff in RDI, calling print, so on, calling print. Right? That's what we want subroutines for, to reduce all the work we have to do to make all this stuff work. All right. We put the first and only argument in RDI, and we just call print. And how does it work? Well, if you look down here at our read-only data section, you'll see we have these strings. They have new lines at the end, and then they have zeros over here. So we don't have their length specified, but we do have them null terminated. And in fact, the print function is going to infer the length by counting up to the null terminator, and then it's going to pass that information as the length argument to the system call. There you go. So the first two instructions, XOR EDX with itself, that is going to set the 32-bit register EDX to 0, which will 0 extend into RDX, so the entire RDX register is now set to 0. Then it's going to decrement EDX, resulting in the 32-bit register EDX holding the value -1, the 64-bit register RDX holding something that's not -1. But that's okay. EDX will hold -1. This is a fast way of putting -1 in EDX. It uses fewer bytes than if I had used a 4-byte -1 literal. Just a weird assemblyism. So here's the top of my loop. What does my loop do? Well, the first thing I do is increment EDX. So it started out -1. Now it's 0. I compare the byte at RDI. That's the thing that we're provided as the argument. That points to the start of one of these strings. So I compare that byte plus this offset right here to 0. Now, you may wonder, well, that's 64 bits, and you said that this was 0 extended. It was wrong. The first thing we did was increment this, so now it holds 0. The only reason for setting it to -1 is so that this will set it to 0. This is going to effectively be unsigned, and we're fine. So the string start address plus the byte index starting at 0, and we compare that to 0. We say, do we have a null? Do we have a null? Do we have a null? Until we find it. And if it's not equal to the null, we go back to the top, we increment EDX, and we just keep going. So this holds the base, and this holds the offset into it, right? This is like the index with a scale of 1. So when we're done, EDX is going to hold the length of the string because it's going to be the position where we first found the 0. That's great. So then we put 1 in EAX. We put RDI in RSI, right? So EX is the system call. It's right. This is the buffer. Put in RSI. EDI is the file. They're out of order here. EDI is the file descriptor. That's standard out. We stick in EDI. And we've already made sure that EDX holds the length, which is the argument, and we do a syscall and return. There you go. Nothing magical about the order in which we set them. We just have to be sure they all get set correctly, and they do. And that will then print out our string using this to find the length. There you go. That prints our string. Great. That packages up all that machinery for the system call in a convenient way. And so then we can print message 1, print message 2, print message 3. And notice how we get the address into RDI. I could have just said move RDI and message 1, and that would have worked. But instead, I'm using load effective address to take this address and load it into RDI. This is much more common. This is what you will typically see. Either way will work. That's just a little more common. Then I do the exit, and we're done. So this walks through a little bit more of it. There we go. Talk about LEA. Then I can assemble it and take a look at it, and here's what it looks like. And notice that this is assembled and linked, so I actually have virtual addresses for this stuff. Okay? And the data has an address. It's sitting over here, so you see that I'm loading the actual addresses of the strings, here they are, into RDI and then making the call. So a good question is, what exactly happens when I call print? So let's pick one of these calls. This one right here. Okay? I've loaded a value into RDI and now I'm calling print. What precisely happens? What is RIP when this instruction executes? Well, when this instruction executes, RIP is here. It's holding this value, 401029. So we expect that to get pushed. We expect that to be loaded into RIP. Okay, that is up here, and we expect this code to execute. When the returns hit, we expect RIP to be popped off the stack. It'll be this value right here, and so the next fetch will happen here, and it'll be this instruction, and it will continue ahead. That's what we want it to do. Let's see if that is in fact what happens. So here's our call instruction. When we call it, the current instruction pointer is pushed onto the stack. There is the current value of the instruction pointer. We push it on the stack. There it is. Boom. This would be an 8-byte section. I'm just abbreviating it here. Next, the argument to the call is loaded in the instruction pointer. We know it's this, so we expect this value to go right here. Boom. There it is. And now it does the print procedure. When we return, RIP will be at this value. That's the address of the instruction following the return. And what we'll do is discard this value and override it with what we pop off the stack. So we'll then pop the stack, okay, put that value into RIP, and we're ready to resume with the instruction following the call. And the old value is still here on the dirty stack. And That can be useful information if you're hacking around. You can find out where certain calls happened. And that may be useful to you if you want to dynamically tinker with a program. So, we talked about how you call a routine, how you get back from it. We haven't talked at all about how you pass information to it or how you get return values back from it. There is no machinery for that. It is all going to be done by convention because that's how we do things. So how do you pass arguments, get return values? Depends. How do you want to do it? Well, you can do it. You can do it any way you want to do it in your code. But if you want to call somebody else's code, you have to use the method that they expect you to use. Right? If you don't use that, then their stuff's not going to work correctly. And the way in which you organize arguments and expect to find return values, etc., that is called the calling convention. And it has a lot of information in it. Some of the information is what should be the order of the arguments on the stack. Let's say we put arguments on the stack. In what order do we put them? Do we push the first one, push the second one, push the third one? Because then the thing we call could pop the third one and then pop the... it seems backwards. In most cases, you push them in reverse order. Just the standard that is often used. How do you access the arguments on the stack? Given that the return address must be at the top of the stack when return is executed. So let's say you want to pass them on the stack. You push, 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 and then you do a call which pushes the return address on there. So you got to be careful. The return address is sitting right there. It's at the top of the stack. I can't just pop things off or my return's not going to work. So I got to be careful with that. Could I put the return value in a register? That might work. Who is responsible for cleaning up the stack if I push stuff on the stack? And if you call my routine, can I modify any registers? Your code is using registers for certain things like weights and indices. And if I mess those registers up, nothing magically fixes them when I return. Right? They don't go out of scope and get reset. They're just registers. So we have to decide, do I get to use any register I want? If I want to use RCX, can I just use it? Or do I have to save its value and then restore it? What should it be? So all those are questions that have to be answered by calling convention. So the idea of putting your arguments on the stack and having the return value in EAX is the way things are often handled in the 32-bit x86 world. You've seen x86 code, that's the way they usually do it. This is called the CDECL calling convention, and it started with, no surprise here, the language C. It's a really good, simple way to do things. And sometimes in code you'll see like underscore CDECL, or sometimes you'll see this in code that's not C. You'll see that someone will declare it to be C, so that we know the calling convention being used is the C calling convention. Okay. Now, so I'm going to use the words callee and caller. I'm going to try to enunciate them clearly. The caller is the one who has the call instruction and calls out to another subroutine. The callee is that subroutine. If the callee, the call procedure, if it's responsible for cleaning up the stack, this turns out to be a special version of the CDECL calling convention called the standard call calling convention, and it's all over the Win32 API. That's how it works. It's easy to spot this because when you see a return, it will often have an argument. It's an argument to return. So return 16. Is return 16 returning the value 16? No. Return 16 is saying do the return and then deallocate 16 bytes off the stack. We'll see how this works. But that's the standard calling convention. Great. Arguments on the stack are a time-honored way of doing it. Suppose you have 3 arguments. The traditional way to push them on the stack is right to left. So we push arg3 first, then we push arg2, and then we push arg1. There we go. And then we do a call, and the return address sits right there. Now, where are these things? Well, we can reference them with respect to the stack pointer, right? We know that they're at, and it says RSP, but this is the 32-bit world, so it should say ESP. Apologies. We know that arg3 is going to be 4 bytes up because the return address in the 32-bit world is 4 bytes. So RSP plus 4 will take us here, plus 8 and plus 12, and that allows us to go and reference these D words that are found at these locations. We know the D words because we said they were 32-bit ints. Now on return, we use the instruction ret12. Ret12. Okay. What does that mean? That means we return, so we remove this 4 bytes and stick it in RIP, but then we also add 12 to the stack pointer. So once we pop the return address, we're pointing here, and then we add 4, 8, 12, and we've removed the arguments. Okay, great. and there you go. Now, the downside to using the stack in this way means if I want to access the arguments, I have to do memory reads and memory writes. If stuff gets out of the cache, I have to load it back in. It can be a problem. They can be slow. You know, it'd be faster if all my arguments were in registers. That would be faster. In a world where I have very few registers, that's not practical, right? Because I need my registers to hold the values of the program. I can't just store them all or push them all or do something else with them when I want to call something, right? Now, but in a world where I have lots of registers, I don't care as much. And I'm happy to use registers to pass values back and forth. And in the 64-bit world, that's what we do. We use registers. It's generally faster. It's generally faster to put the arguments we want in the registers. And we can still use the stack, right? We only have so many registers to use, so if we run out of registers, we'll just put stuff on the stack at that point, and that's fine. But we'll use registers for most cases. Some platforms, ARM comes to mind, actually use a special register to hold the return address from the subfunction. That's fine. That's fine. We will still push and pop it. That's the way it'll work. Here is a quick snapshot of part of the AMD 64 calling convention. This is a really important piece of information. You should keep track of this particular slide. It's useful stuff. Linux, macOS, Solaris, most operating systems that are built to work on the AMD 64 architecture use the AMD 64 calling convention. Why wouldn't you use it? This is the people who made the stupid architecture have published this. Well, you wouldn't use it if you were Microsoft, because you'll make your own, and that's fine. Again, everything's by convention. We should definitely have lots of competing conventions because that makes the world more fun. Because Microsoft sits on the UEFI board, UEFI also uses Microsoft's calling convention. What do they look like? You can go to those links and take an in-depth look. You'll find, I think, my opinion, that the AMD 64 calling convention is fairly simple, and the Microsoft one is rather tedious. Just my opinion. So what do we have here? We have a list of registers, and you'll notice that there are the usual registers RAX, BX, CX, DX, and so on. There are the XMM registers. Right? These hold floating point values. There are these temporary registers. There's these. What is all this stuff? Again, lots of stuff. Lots of stuff on the processor. Don't worry too much about that other stuff down there. Okay? Focus on this stuff up here. So over here we have an important column. This tells me, do I need to, or am I expected to, preserve this value across a function call? So I'm writing some code. You call my code. Can I just use RAX and not worry about what happens? Yes, I can, because it's not preserved. It's not preserved. What about RBX? No, I can't. It has to be preserved. That means I have two choices. I can either not use RBX, or I can save the value of RBX and then restore it before I return. Okay? Those are my two choices. What about the third choice of changing its value, returning, and letting the caller then... Sure, I can do malicious stuff all day long. But following the calling convention, I won't do that. You have to be careful. RCX, RDX, don't preserve them. RSP is the stack pointer. Yes, you have to fix the stack pointer before you can return. You can't just randomly set it off into space and then call ret. Who knows what's going to happen? So don't do that, right? Stack pointer has to be preserved. And in fact, we'll see. We're going to use it, right? We're going to push and pop things in our code. We just have to be sure at the end, before we return, we restored the correct value to the stack pointer. RBP is the base pointer. Most routines use it to indicate where their stack frame ends. We'll talk about that a little bit. It has to be preserved. We will typically set it and then not modify it. We'll use it as our stack frame pointer, and right before we return, we'll restore the caller's stack frame pointer. Now we come to some interesting stuff here. RSI, RDI, all these. No. Now there's information in here that might be worth reading, so let's dig into this just a little bit. RDI used to pass the first argument to functions. Interesting. RSI is the second. RDX is the third. RCX is the fourth. This is sounding like the sequence we use to pass arguments to a system call, and in fact it's almost the same. It's almost the same, slight difference. We can pass floating point arguments. They go in XMM0, XMM1, 2, 3, 4. Those are used to pass the floating point arguments. And with a return value, with variable argument, it passes information about the number of vector registers used. We'll see that with printf. Otherwise, it's the first return register. What else? Second return register is down here in RDX if we need a second one. Where's the third one? There's not one. There's not one. Okay. TLDR. Integer and floating point arguments go in RDI, RSI, RDX, RCX, R8, and R9 in order. How does this differ from the calling order for system calls? Right here. Instead of RCX, for system calls, we use R10. Just because. It's kind of convenient. RCX is usually a count register being used in your routine. It's kind of nice if the system call, we can call that without having to corrupt the count register. Floating point arguments go in these. We can have up to 8 of them. They go in that order. What if I have more stuff? Well, then I can put them on the stack. Return value is an RAX. That's 64 bits. It can hold a pointer, an integer, a byte, whatever. You just have to know how to interpret it. If it's a floating point number, it goes in ZMM or XMM0, or it could go in those if it's bigger. We might use the second register as well. We saw that RDI is that second register. And you have to make sure you do not modify, or you save and restore, right? Those are your two options. Don't touch it. If you touch it, put it back where you found it. These guys right here. And that's the TLDR for the AMD 64 calling convention. Is that everything that's in it? Oh, heavens no. Go and read it if you really want to know. This is, in practical terms, pretty much all you need to know. An example of it. So here's a simple function. look at this guy. It's super complicated. We go and get int types, so we can say unsigned 64-bit integer. It's a function that takes a value and returns that value. Wow, this is not a complicated piece of code. What does the compiler make of it? Well, here's what the compiler produces. And let's walk through this and see what happens. This is using GCC. So we see GCC with a -c just compiles, and then we do an obj dump of the .o file, and this is what we get. The first thing we see is this, NBR64. What is that? That is used for branch protection. A protected branch has to go to an address that contains this sequence, or else it triggers an exception. This sequence is a no-op. It's only there if you want to use branch protection. Otherwise, it's just a no-op. And in fact, if we would compile it with Clang, Clang by default doesn't put that stuff in. So we notice we get the exact same code, just minus that first instruction. It's kind of fun. So let's go back and take a look at what's happening in here. We know from the calling convention that RBP is a callee saved register, so we have to protect it. It has to be preserved across function calls. So the first thing we do is we push our caller's base pointer, and then the last thing we do is restore our caller's base pointer. And this is really common. That's a pretty normal thing to do. Okay. If we know we're not going to modify RBP, if we are going to not touch it, we don't have to save it. But we have to be sure we know we're not going to touch it. Okay. What about this? The stack pointer. So it's traditional to move the stack pointer at this moment into RBP, because the RBP now points to the base of our stack frame. This points to the highest address of the stack that our routine owns. The end of our stack frame. Okay. And that's fine. Now, normally at the end, we would move RBP back into RSP. We don't modify the stack pointer anywhere in here, and so we don't need to do that. So normally you use something like RBP moves back into RSP. You don't have that here. The compiler didn't think we needed it, so it didn't put it out. This is the common wrapper on procedures. Push RBP, put RSP into RBP, do some stuff. Don't modify RBP, but you can modify the stack all you want, because at the end, we fix it. So suppose I come in here and I just do crazy stuff to the stack. It doesn't matter, because I'm just going to straight up set the value back to what it should be. So I could come in here and do push, 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 never pop anything, and then bam, it's set back like it was. And then I pop RBP off the stack, and that's going to work because I already fixed the stack. I fixed it here, and then it's fine for me to pop it here. Make sense? Hopefully that little sequence of things makes sense, and then I return. This is super common. It's so common, there are actually specialized instructions in the x86 instruction set to do that. There is one called enter and one called leave. Leave does this. Enter does a bunch of stuff that we don't care about. It's more complex, it's slower, it can allocate memory and do other stuff. It's almost never used. You'll almost never see it. I'm shocked whenever I see it. I'm like, wait, are they using that? Most of the time, you will see some of this and some of this. You'll see both. So I went through all the ELF binaries on my Linux system, and I found 15,000 instances of enter, but I found almost 200,000 instances of leave. So enter is not very widely used. And in fact, most of these are code in just a couple programs. You don't have to use those. I looked at the Python 3 executable on my system. It's a pretty good size executable. No instances of enter or leave. Just not there. Didn't use them. It used the move and pop for leave and the push and move for enter. So I'll switch back and forth at random in this course between doing this kind of stuff and doing leave. So you'll see them both. I won't use enter. All right. So far, life is simple. You want some space in the stack, you move the stack pointer, you subtract some value from it to allocate space in the stack. Now you can put stuff in and out of that memory. Great. So, it's so great and so simple. The only thing we can do now is screw it up, and that's what we do with something called the red zone. So the red zone is the 128 bytes below, as in negative, below RSP. So these are the 128 unallocated bytes below the stack pointer. And those are called the red zone. And you can use them as scratch memory. You can just stick values in there and do what you want to do with that as if you owned it, because you basically do. Is that a good idea? If you're going to call another routine, it's a terrible idea, right? Because the first thing that will happen is the address you call will get pushed on the stack, which will overwrite part of the red zone, probably screw your stuff up. It's a bad idea. But if you are what's known as a leaf process, right? You're a process that gets called, you're not calling anyone else, it's fine for you to use the red zone. And you don't have to modify the stack pointer to use it. Okay? Yeah, I know, it's pretty crazy, huh? There's a guarantee that interrupt and exception handlers will not override it. Those 128 bytes. Okay. So normally you would reserve stack, you'd have your temporary variables in the reserve stack, and when you're done, the stack pointer gets set back and everything's fine. But you can use the red zone if you want, and in fact, the little program that we compiled up here uses the red zone. Does it really? It does, right here. It's got a local variable. RDI holds the first argument to the function according to the AMD calling convention. And we take it and we put it at RBP minus 8. Now, where is that? Well, up here we set RBP equal to the stack pointer. And so this is really the stack pointer minus 8. And we know that when you want to allocate stack, you subtract. So this is below the stack. This is in the red zone. This is in the unallocated area below the stack. It's fine to use it. We're not going to call any other functions, so it's okay. If we called another function, we would certainly screw that up. All right. So we stick the argument in here. The next thing we do is we take the argument out of there and put in RAX. Why? Because that's the return value. But we expect the return value to be in RAX. So the argument was an RDI. We then stick it in here. We then move it from here to here. It's now the return value, and we return. Very literal, okay? That's how it works. Wow, that seems pretty crazy. Normally, like I said, you would reserve some stack. Let's say you wanted to have 4 8-byte values on the stack. You would do something like this, sub RSP, and then you could do 8 times 4. NASM can figure out that's 32. And now I have room for 4 variables. They are these locations, because remember, I'm not going to change RBP, and if I call something, they will fix RBP back to where it's supposed to be, so I can always reference them this way. And there you go. But we don't do that here because we use the red zone. Anything to make things more complicated. So, why did I use this intermediate value? Well, it's because that's how code that you haven't optimized is going to work. And it's going to work that way because it's easier to debug, etc. So if I optimize it, what happens? Well, really all this is doing, I'm taking RDI and I'm moving it into RAX by way of this temporary space in the red zone. So really all I need to do is move RDI into RAX. And I can just do that right there. I could have just done that with one instruction. What if we optimize this program? Let's do it. Let's run it with -02, and what do we get out? We get this. There's our branch protection. There's that one move instruction. Take the first argument, put it in the return value, and return. That's it. That's this whole function in optimized assembly. So, the point here is nearly everything is by convention, and there are lots of different options. If you want to use other people's code, you have to follow the correct conventions. And they can vary. Right? If I want to call Fortran code, it's a little different. If I want to call C++ code, a little different. I have to follow the correct conventions. But most of the stuff in the Linux world is going to follow the 8064 calling convention, and that's how I'm going to operate. You have to follow the conventions, or you can break the conventions and see what happens. Right? Conventions are things we assume are going to be true. Vulnerabilities often happen when there are unenforced but assumed conventions. Right? We're assuming I'm not going to maliciously manipulate the stack pointer and then return, but I could. You're not going to change my base pointer. So remember, I might store my local variables on the stack and reference them with respect to the base pointer. Well, what if I copy since I know what your base pointer was because you called my function, you told me where your local variables were, I can go and move the base pointer to point somewhere else, and in fact, I can then find the return address for your return address when you want to return, and I can point that somewhere else, and I can control where you go when you return, or I can point to a new set of variables, or I can do any number of other perverse things. No one would ever do such a thing. That would be mean. Okay? Vulnerabilities often happen when there are unenforced but assumed conventions. We have a third homework. Given what you know now about how things work, the homework is to take your Hamming weight code and turn it into a function that can be called from C. So here we go. Here's some C code. This is a little main function. And you see we have int types and standard I/O. Look at this right here. We have Hamming. It takes a 32-bit value. It returns a 32-bit value. So it's going to have something in EDI and something in EAX. There you go. But I don't say what it is. This is just a prototype. Someone has to provide this function. Could be anybody. Could be C, could be assembly, could be Rust. I don't care. Here's my main function. I'm going to look for an argument. I'm then going to print some stuff out. I'm going to go ahead and call that Hamming code down here and print the result. This code's available up on iLearn. How are you going to do this? You're going to put your code in hamming.asm and you're going to upload that as a solution. What will that look like? It's up to you. Next time, we're going to talk about ELF files, relocations, linking, and position independence. So, when you have questions about the homework or anything else, let me know. This was a lot to go through today, but I didn't want us to get too far behind. Hit me with your questions. Happy to answer them.